In section 2.3, we're discussing techniques of differentiation, and in the last video we talked about the power rule. We talked about the binomial expansion. We're going to use binomial expansion now to show what the power rule is or why it works, and then from that we'll just, without a proof, go on to what's called, your book calls, the extended power rule. Now recall that if we had x plus h raised to the power n, all right, that was going to be x to the n, 1 times x to the n, remember the first entry of Pascal's triangle, plus n times x to the n minus 1, one smaller power of n, times h, plus terms with a common factor of h squared. And what we want to do is we want to find the derivative with respect to x of x to the n. So, the derivative by definition is the limit as h approaches 0 of f of x plus h minus f of x all over h. In this instance, since x is f of x is x to the n, this will be the limit as h approaches 0 of x plus h raised to the nth power minus x raised to the nth power, all divided by h, the change in f over the change in x, which was h. All right. Because of the binomial expansion, we saw that x plus n, h raised to the nth power is this expression x to the n plus n x to the n minus 1 times h plus terms with h squared. And I'll just abbreviate or shorten it to that. That expression, that's all of this, minus x to the n, all divided by h. Well, we see here that there's an x to the n and a negative x to the n, so they will subtract off. And notice these terms that we haven't written out all have at least x to the h, at least have h squared factors in them. This first term has a factor of h, and so all the terms have factors of h. We could take a factor of h out of every one of those terms. We haven't written them all now, but we could if we did write them. And so we'll have an h times, well, let's see, what will be left here? Well, we'll have n times x to the n minus 1. The h will be taken out, plus, then we'll have terms. Now, they had at least h squared before, but we've taken one of the h's out, so now they'll have at least h. And we'll divide by h. The h's cancel, and we're left with this limit. Right. Now, because of this limit, or because all these terms have h in them, they all might be something like 7x to the third times h, or whatever. All right, if I let h go to 0, what happens to that term? Since it has an h in it, the term goes to 0. So all of these terms in back here will go to 0. So I'll be just left with n times x to the n minus 1 plus 0. So we have this statement. This is the statement of the power rule. If f of x is x to the n, then f prime of x is nx to the n minus 1. All right, notice if f of x is x to the n, to get its derivative, we take this exponent, n, out in front, and then reduce the exponent by 1. And this works for n is equal to 1, 2, 3, and so on. Okay? Let's look at a couple of examples. Suppose f of x is x to the 7th. We want to find f prime of x. Here the n is equal to 7. So f prime of x is, remember, the old exponent goes out in front, and the new exponent is one smaller. It'd be 7x to the 6th. It's pretty easy. All right, suppose f of x is x to the 25th. What is f prime of x? Well, f prime of x, here the n is 25. F prime of x is, well, the old exponent comes out in front, and the new exponent is one smaller. All right. Without proof, we'll state what your book calls the extended power rule, and the extended power rule says the same thing works not just for the integers 1, 2, 3, 4, and so on, values of n, but it works for any real number exponents. It works for any real number exponents. We basically get the same power rule. All right, so let's take a look at this, what we can say here. So now if f of x is 1 over x squared, let's find f prime of x. Well, if f of x is 1 over x squared, all right, then another way to write f of x is, of course, x to the negative second. Notice negative 2 is not one of those values, 1, 2, 3, 4, and so on. All right, then according to the extended power rule, f prime of x is, well, the old exponent comes out in front, negative 2x, and the new exponent is one smaller, negative 2 minus 1 is, of course, negative 3, so it would be negative 2x to the negative third. And since they gave us this as a fraction, we'll return it as a fraction. It'll be negative 2 over x cubed. And there's the derivative. Let's try one more. We've already taken this, taken this derivative, but let's do it now using our extended power rule. All right, if f of x is square root of x, find f prime of x. Well, if f of x is the square root of x, f of x can also be written as x raised to the power of 1/2. Notice we have a 1 in here. This is a square root, so the index, although it's understood, is 2. All right, and this will be the power. This would be x to this power is the numerator. The index of the radical is the denominator. Okay, so according to the extended power rule, all right, f prime of x will be the old exponent comes out in front. The new exponent is one smaller. So this would be 1/2 x to the negative 1/2, which is 1 over 2 times x to the positive 1/2, which is 1 over 2 times the square root of x. All right. Now, students often ask me, do I have to put it back this way? And the thing is, I say you would have to know how to put it back that way. I won't always mark it off if you don't, but you should. It's not an excuse to try and avoid learning how